Program, we will be looking at 3 aspects of artificial intelligence. First, we'll discover how a computer works. Then we'll explain how microchips function. And finally, we'll introduce you to 2 medical expert systems. During the 17th century, scientists began looking for ways to make counting faster and less tedious. The great-grandfather of the computer was Blaise Pascal, the French philosopher and mathematician. His invention, the Pascaline. Inside, a gearing system that added and subtracted. 2 centuries later, in London, Charles Babbage invented the analytical machine. His device could be programmed using perforated cards. It could even store transactions to be carried out. The problem was that at that time, there was no way it could be built. This austere-looking man is George Boole. He too contributed to the invention of the modern computer. He dreamt of bringing all logical reasoning down to a series of questions that could be answered by a yes or a no, a 0 or a 1. For many years, the works of Boole and Babbage remained mere curiosities. Nonetheless, it was thanks to them that 20th century engineers were able to construct the computer we know today. The computer, first used for military purposes, has now made its way into every nook and cranny of society. It is a machine we consider both mysterious and all-powerful. Yet the computer only does what we tell it to do, and the way we dictate it be done. In fact, while highly complicated, the computer, devoid of intelligence, is but an electronic slave. What goes on behind the screen of a computer? By means of a keyboard, a mouse, or a graphic tablet, the user interacts with the machine. Whether the user employs letters, numbers, or shapes, the machine receives all the data in binary language. This numeric language consists only of 0 and 1. And since the information circulates through a computer in the form of electrical current, the zeros and ones correspond to an absence or a presence of electrical impulses. The data transmitted to the computer is temporarily recorded in what is known as the computer's random access memory, or RAM. RAM can be compared to an exercise book in which you write, erase, cut, and paste at will. When you write a text, for example, the words are recorded in that memory, so you can erase words, replace them, move entire paragraphs around. RAM is a flexible memory. But computers have another type of memory called read-only memory, or ROM. It is in the ROM that the basic instructions that make a computer work are stored. ROM can be compared to an instruction manual. It's called a memory because the instructions it contains are usually immovable and integrated in the computer's very architecture. Thanks to its directions for use, the computer can follow the instructions of a software program, which constitutes, for all intents and purposes, the computer's brain. Without a software program, the computer is just a useless box, or hardware. Once software has been introduced into a computer, it's a little as if a brain were put into a cranium. Software, designed by computer experts, processes information provided by the user, carrying out a series of logical operations according to a plan. We refer to it as a software program. A software program gives life to a computer. Its ROM becomes active, and the program is able to process the data the user sends to the RAM. A same computer is able to obey the instructions it receives from various software programs, be it word processing, accounting, data management, graphics, or games. The applications are virtually unlimited. Once the job is finished or the user wants to take a break, the work already completed can be stored in the same way that sounds or images can be recorded on magnetic tape or cassette. The data is simply transferred onto tapes, or floppy or hard disks. As a rule, the keyboard, mouse, or graphic tablet are the computer's points of entry. The screen and printer are usually its exit points. The images, data, or words displayed on the screen can be reproduced onto a printer's paper or onto magnetic tape. The computer, regardless of its power, remains a tool that obeys the orders we give it. Nowadays, computers can fit into a briefcase. They're flexible, portable, and inexpensive. But it was not always so. The first computer was the ENIAC. It weighed 30 tons and cost several $1 million to build. It was during the Second World War when the United States Army needed a machine able to quickly calculate the trajectory of its new missiles. Unfortunately, the ENIAC had its share of drawbacks. It took up as much space as a two-car garage, and it had to be programmed by hand. And every day, one of its 18,000 vacuum tubes would burn out. A few years later, the vacuum tubes of the early computers were replaced by transistors, themselves later replaced by microprocessors or silicon chips. A chip is a labyrinth, but you can manage to find your way around. Modern computers can perform millions of operations in a second, and they can do this thanks to microprocessors or silicon chips. Today, microprocessors can program a broad range of machines, including automatic coffee makers and digital watches. Inexpensive, silicon chips are made from one of the Earth's most plentiful elements, sand. Silicon was chosen primarily for its semiconducting characteristics. Silicon is about halfway between electricity-conducting materials like copper and insulating materials like rubber. What makes silicon so attractive is the fact that its electrical properties can be fashioned so as to make a chip's minute surfaces more or less conductive. This meant that it was possible to duplicate the electronic components of the first generations of computers, like transistors and resistors, in microscopic format and at much less cost. Chips are designed to perform the tasks we want them to. Those used in a camera, for instance, are designed differently than the ones used in a car's fuel injection system. The architecture of a silicon chip can be compared to a city street map with its streets, intersections, forks, and stopping areas. The silicon makes up the layer supporting the city. The streets are made of minuscule lines of electric conducting metals such as aluminum. Like viaducts and elevated highways, the aluminum lines can be superposed. The electronic components of the chip, such as the traditional transistors and resistors, were produced by altering minute surfaces chemically. These minute silicon surfaces act somewhat like traffic signals or lights. When an electric impulse travels on a chip, it follows the path indicated by an aluminum wire. On the wire, the electric impulse meets a minute, chemically modified silicon surface. This silicon surface can, for example, act as a transistor and send the electric impulse onto another aluminum wire. Thus, thousands of electronic components direct the traffic of electrical impulses. In this complex network, electric impulses travel almost as fast as the speed of light. Computer-aided design is used to create a chip. This method helps not only to determine the chip's architecture, but also to simulate and check how well it works, even before it is manufactured. From the configuration thus obtained, a pattern is drawn up in which every line and electronic component is clearly defined. Next, various masks are pasted on a silicon disc by a photo engraving process. This makes it possible to cover or uncover certain microscopic silicon surfaces with a photosensitive resin so that they have special conducting properties. It's like a stencil whose letters are either hidden or uncovered. Creating a chip requires the application of several masks. Thus, with every mask, the various parts of the electronic components add to each other on the chip. Several hundred chips can be produced, usually 6 millimeters wide, from a silicon disc. So through various chemical alterations, the equivalent of thousands of transistors and resistors can be reproduced on one single chip. The last stage in making a chip is called plating. It involves connecting all the electronic components of the chip together. Usually, aluminum is used as a binder. The aluminum lines can be as little as 2 microns thin. Just to give you an idea, the diameter of a human hair is about 100 microns. During fabrication, the slightest dust particle falling on the silicon disc can render a chip completely inoperative. That's why the technicians wear suits, gloves, and masks. Every step in the making of a chip is so delicate that the atmosphere in a plant must be 100 times purer than in a hospital operating room. Computers are fine for processing vast quantities of data and for accomplishing any series of simple and repetitive operations in record time. But computers can't replace man when experience, intuition, and imagination are needed. Nowadays, instead of trying to imitate the human brain, computer specialists are working on what they call expert systems. To create an expert system, a knowledge engineer sits down with an aeronautics specialist, for example, and asks him questions about everything he knows. The objective is to obtain a computer program containing all the experience and knowledge of a lifetime. Expert systems provide access to the greatest specialists in their fields. In emergency situations, medical teams often have to react within minutes. The survival of a patient often depends on how fast and accurately they act. But with the proliferation of drugs and the improvement in medical knowledge and treatment, the work of the practitioners is becoming increasingly complex. The computer, through its medical expert systems, will soon be able to help doctors faced with emergency situations. The middle of the night. A person has had a heart attack. Pulse is at 0. The patient is not breathing. The emergency medical team has but a few minutes to get the heart beating again, or else the patient will either die or suffer serious after effects. The team, no matter how competent, is under considerable stress. Stress that could be the cause of irreparable errors. The cardiorespiratory resuscitation expert system, on the other hand, remains imperturbable. When it starts up, the system displays 9 information windows, a dialogue window, and a clock. The first 9 windows display the patient's vital statistics, blood pressure, pulse, breathing, together with any information on electrocardiograms or drugs administered at the time. The medical team keeps the expert system informed of the treatment it gives at all times by using a keyboard. In return, the expert system asks the team for information it requires to perform its reasoning. The doctor can, at all times, via the dialogue window, ask the expert system its advice on what his next move should be to resuscitate the patient, whether by electric shock or medication. Further, the expert system can justify the suggestions it makes. Throughout this man-machine conversation, however, ultimately, it is the attending physician who has the final say on the decisions to be made. Once treatment is completed, the expert system produces a comprehensive report of all the care the patient received. The integrated clock even indicates the precise moment when each procedure was carried out. Soon, hospital emergency wards will be fitted with this equipment. Also, because it is portable, it could quickly be set up in a patient's room in an emergency. Computerization should soon help lower the risks of errors made in emergency situations. Currently, research on software applications in the medical field is booming. One such application has already been tried and tested for muscular rehabilitation. A patient following muscular rehabilitation treatment, following an injury or surgery on an arm or a hand, has to visit a physiotherapist 2 or 3 times a week. Since the treatment can last over a fairly long period of time and the exercises are tedious, patients often lose interest. A new computer tool now offsets such problems and lowers the number of sessions required with the physiotherapist. When the patient has reached the reinforcement stage, he is sent home with a monitoring device, via electrodes that the patient puts on the weak muscle area, and a handle that picks up every muscle contraction. The monitoring machine records all the physiological variations during each session of exercises. An electronic display enables the patient to monitor his own progress every time he contracts his muscles. After a few sessions at home, the patient returns to the physiotherapist's office with the monitoring device, which is then hooked up to the specialist's computer. The computer interprets all the data collected and shows the progress made in alphanumeric or graphic form. Analysis of the progress report enables the physiotherapist to tell the patient precisely how the treatment should proceed. The monitoring machine can also be connected to the specialist's computer by telephone line, further reducing the number of sessions with the physiotherapist. Studies have shown that patients on the expert monitoring system were more motivated to pursue their treatment and obtained better results than the control group. High hopes ride on medical informatics, but it will still be some time before our family physician is replaced by a machine with a silicon heart. Teaching a computer something as simple as distinguishing apples from oranges or eggs is extremely complex. Artificial intelligence remains a dream, but there are scientists the world over who believe it is one that will come true.